Okay, so now let's solve the problem using linear triangular elements. Here you can see the mesh. We generated this mesh before, and this is our problem. The value of U solution function is equal to V electric potential. Alpha x is equal to alpha y is equal to 1, and the value of beta and g are equal to 0. So even I can use our first code, finite element try 1, right? I will show you how we can solve two-dimensional problem considering the same procedures. So I copy this part and boundary conditions, right? Copy finite element 2D try 1, and I paste this here. So first of all, we should allocate memory for a stiffness and load vector. Then we should construct the stiffness matrix and load vector. So here you can see for each triangle element, we have 3 mesh nodes, right? Also, we had these values for M and T and F and P, these values, right? So here I can write index I and index J are 9 by 9, and the value of K is 9. You know why? Because for each mesh element, we have 3 mesh nodes, and this is the stiffness matrix. We have 9 elements. So this is V1, V2, and V3, right? So we should store index I and index J of 9 elements and the value of a stiffness matrix for 9 elements. So this is index I, index J, and the value of K, right? So also let me calculate xij. As you can see, we should calculate the value of, for example, for M11, that is equal to M21, we have this Y23, Y31, X32, X13, and X13 here, X21, X21, X13, X21, X32. So we should calculate these terms. I write here X13 is equal P1 and connectivity list, and I write this. For first, actually, how we can extract indices of first points of all mesh elements, like this, right? Here is the connectivity list. If I run this code, let me place a breakpoint here. Right. I write connectivity list, and this is connectivity list 1 and column. So these are indices of first point of all mesh elements, right? So I can write this. Actually, we are going to use index programming. Index programming to make calculations much more compact, right? So this is, excuse me, x1 minus x3. So this is x1 3, right? Instead of writing for loops, I can write for loops, right? I can write for loops here and use indices, but this is much more compact and faster. So this is x1 3 and x2 3 is this. So what is the value of y2 3? This is 2 and this is 2. What is the value of y3 1? This is 3 and this is 1. y3 1. So is it clear, this line of the code, or do you have any question?
It's clear for now. I'm happy to
Right. You know,
revise them.
I don't want to write for loop because later we will solve large problems. So using index programming, we can write fast codes and we can calculate the value of m11, m12, and so on for all mesh elements. So similarly, I can calculate these values m22, m33, and this is m11, and construct my stiffness matrix. So here I write the value of k, 1, and the rest. You know, I have this stiffness matrix for each mesh element. I do this index 1, 2, 3, 4, 5, 6, 7, 8, 9. I should store 9 elements for each mesh element. So actually I allocated memory like this: 9, 1 to 9 by number of mesh elements. NE here is equal size of connectivity list and 2. So index I, index j, value of k, right? Here I should calculate y23, x32, y23 and x32. And as you know, x32 is the same as x23, but we should multiply a negative 1, right? Here, x32 is equal to negative of x23. So you don't have to repeat the calculations again and again. So we have a connectivity list, and I can write something like this for index I and index j. I write index I is equal, here is for one-dimensional problem, right? We considered 1, 1, 2, 2. Actually, the way that we calculated and stored the data. So here is 1, 2, 3 local points. Actually, this is our element: index 1, index 2, and index 3. Also, this is 1, 2, and 3. So, what is the index I of this point? is index I is 1, right? So I can write here something like this. Connectivity list of 1 and, excuse me, right, 1 and the rest. So later I will sort the code. This is 1 and the rest. First row. Let me copy and paste. 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 And I write index j, ij. Again, this is for the first, second, and so on. And I paste this value here. Here. The index I of this element is 1. Index j is 1. Index I of this element is 2. Index j is 1, right? So you need to focus and put time. Well, this method of programming is very, very effective. So index I is 2 and index j is 1. For this point, actually 1, 2, 3, 4, 5, and so on to 9. So here I write value of k for the second element. So what is the value of k for the first element is this expression. This is 1, this is 1, this is negative. AE is the area of element. So I write here negative 1 divided by 4 times AE. We didn't calculate AE and we should calculate the value of AE times this one, y23 squared. I write y23 squared plus x32 squared. x32 squared. So let me calculate this also here. Later we will refresh the code. y23 and right. So I copy this and paste here. What is the value of M21? Right? This one. M21. M21 is this one. Alpha x times this expression y23 x y31 times y31 x32 times x13 x13. Also consider that M21 is equal M12. This is M12, right? And the index here is 4. The index here is equal to 4. That is the same as this one because the stiffness matrix is symmetric. A stiffness matrix is symmetric. I copy this and paste this here. So I write M11 $sign M21 and M12. Here I write M31. So what is index I and index j for this point? Index I is 1, index j is 2. So index I of this point. Actually, this is 4, 4. This is 1, and this is 2. The index j of this point, 4. So, for this point, this is 3. Enter. This is 3. This is 3. And this is the value of k. Actually, I copy this. This is 3. Index I is 3. Index j is equal to 1. So this is 3, 1. And what is M3, 1? Y2, 3. Y1, 2. 1, 2. X2, 1. So let me calculate Y1, 2. This is 1. This is 2. Right? So also I copy this and I paste it here. M13. M13 is this one. Index is 7. So this is 7, 7, 7. Index I is 1. Index j is 3. So this is 1. This is 3. And the value is equal to this one. The value is equal to index 3. That is 3. Because the matrix is symmetric. 1, 2, 3, 4. So what is the M22, M22, and M33? So this is 5, 5, 5. This is 2, 2, and this is 5. Also, you can see the value of M22. Y31, X13. Y31, X13. For M33, this index is 9, 3, 3. So this index is 9, 9, 9. This is 3. This is 3. And the value 1, 2, 2, 1. 1, 2, 2, 1. So you can check these calculations also later, right? So I need to have x21, this, that is 2, and this is 1, y31, y23, and y12. Right. Finally, we have these two terms, 3, 2, and 2, 3. So I copy this, paste this here. 3, 2. This index is 6. So this index is 6, 6, 6. Index I is 2. Excuse me, is 3. This is 2. And this is equal to 3, 1, 1, 2, 3, 1, 1, 2, 1, 3, 2, 1. 3, 1, 1, 2, right. So write index I, index j value, and we calculated all of these values instead of writing these for loops. Okay, index programming. Now you can construct the stiffness matrix like this. What is the element area? How you can calculate the element area? AE. In our problem, we used a structured mesh. And this was the y, and this was dx. So the element area is 1 divided by 2 times dx times dy, right? So I write here AE is 0.5 times dx times dy. Because the area of all mesh elements are the same, right? The area of all mesh elements are the same. This is a structured mesh. So let me run the code step by step to here, and let's check, right? The value of n number of nodes, as you know, is equal nx times ny. The value of force vector, I run the code. Index into matrix must be positive. So let's check. Index I, we have zeros, and index j, we have zeros. So let's check. Maybe from here, let's check from the first. For 1 1, right? 2 2 is 5 5 5 9 9 9. M2 1 is 2 2 2. This is 4 4 4. And 3 7 3 7 and 8 8 8. Also this is index j, also here, right? Index I, index j, and the value of a stiffness matrix. So if I run this code, you can check index I, this is 0 1 2 3 4 5 6, 1 2 3 4 5 6 for M3 2, M3 2. So M2 1 1 2 3 1 1 3 3 2, finally 2 3, right? 2 3. So this is 6 and this is 8. This is 6 3 2 2 3 is 8, and the value here is equal to 6. 3 and 7 are the same. 6 and 8, 2 and 4, right? 2 and 4, 3 and 7, and this. So if I write full of K, this is full version of the stiffness matrix. So let me reduce number of mesh points 3 by 3, full version of K, right? As you can see, here is the full version of K. So debugging is easier. Anyway, now we should impose boundary conditions to be able to solve the problem. Okay? To be able to solve the problem. So for imposing boundary condition, only we need to find index of these points. Index of these points, right? Copy, paste. We need to find index of these points. And the value of voltage for these points is equal to 1. So what is index of these points? As you know, is from nx times ny minus 1 to nx. So I can write here top points, index of top points is from nx times ny minus 1 to nx times ny. And the value of these points and this row, right, is equal to 0. I should write something like this. For I equal to index, in I and I is equal to 1. So if I write full version, okay, now as you can see, this is correct because we have the value of voltage for 3 top nodes. Is this clear? Applying
Yeah,
boundary
this is clear.
condition, right?
Yeah,
Because
yeah.
like before, actually all elements of the row should be 0. This is 1 and we have the value of voltage at the right hand side. So this is a boundary condition for top points. Okay, we didn't apply the boundary condition for the 0 electric potential edges, these 3 edges, right? So I should apply also boundary condition. I write here bottom points. Actually, we should find the index. We should find, let me place a breakpoint here. We should find the index of these points, right? How I can find the index of these points? I can use this command in MATLAB. I can use this command in MATLAB. Suppose this is a vector 1, 2, 3, 6, and 8. If I write a lower than 3, the result is a logical array, right? And it says the first element and the second element are lower than 3, but the rest are not, right? So I can write something like this. Ground point and write index is equal p1 and colon the first row minus 0 absolute value lower than a really low number 1e minus 6 geometrical error. You know, suppose we have these points on xy plane, these points, arbitrary points. I want to know which of these points coincide with this line. So the x coordinate of this point, for example, and the x coordinate of this x axis should be close to each other, right? So I can write something like this. The x coordinate of points minus the x coordinate of the axis. If this absolute value is lower than a low number, actually this number is geometry error, right? Geometry error. So these are boundary points. Also, I can copy this and write bit or index and absolute value of y, index, absolute value of y and w, right? So let me place a breakpoint here and run the code. excuse me, this is capital W. And right here index. So these are ground points. Actually, you can see this graph. And if I plot something like this, if I use this function print, here I write index of the ground points and also index of ground points here. Instead of this color, I use red. 1 and index, copy, 1 and 2. If I use this notation, you can see I calculated indices of these points. So I need these points, y coordinate equal to 0, excuse me, y coordinate equal to 0, x coordinate equal to 0, and x coordinate equal to 1, right? So I can plot the ground points. So this is 2, this is 1, and this is 1. So run, close, and run the previous command. You can see how we can extract indices of the ground points, right? Using index programming. With few lines of the code, you can solve this problem. So if I want to apply zero electric potential voltage, I should repeat this command here, and solve the problem and finally plot the answer. So this is the value of V calculated by the finite element method. Here we apply it, boundary conditions. So let's run. This is the full version of the K. 1 and 1. So, right. Excuse me. Because index after this line, index is a logical array. We should change it into indices. We should change it into indices like this. Like this. I can write a equal to 1 to number of nodes and a index. These indices. So I explain it a little bit complex. I generate a temporary variable here, number of nodes, and I write index is equal TMP of index. So let's check again. For M11, this is negative, right? And this is negative, 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 and negative here. So I consider it negative 1 by divided by 4 times AE times y23 x32 summation for M22 31 y31 x13 y31 x13 and for 33 y12 x21, right, correct. And now for 21 23 31 3213, that is correct. And for this one 2, 3, 1, 2, this one. Actually 3, 1, right? 2, 3, 1, 2, 2, 1, right? M2, 3, 3, 1, 1, 2, 1, 3, 2, 1. Right, correct. Right. So this is from the analytic solution, and this is from the finite element solution. Here I applied the electric potential equal to 1 for these points. So now let's increase number of mesh points 10 by 10 and run the code again. So if I apply zero electric potential here, also the value of electric potentials for these points will be equal to 0. Okay, so this is the way that I defined for these critical points, right? A copy figure, the value of electric potential for this edge is equal to 0. For this edge is equal to 1. So what is the value of electric potential for this point? You can set equal to 1 or 0. Or you can apply an average value, 0.5. In the finite element method, I applied it equal to 1 in this line of the code, right? But if I write here 2 and minus 1 here and run the code, so in the finite element solution, the value of electric potential also here is equal to 0, right? And this is the mesh, this is the analytic solution, and this is the finite element solution, right? So if I increase number of elements, run. So this is the analytic solution. This is a mesh. Actually, we should zoom because the number of elements is high. So this is the finite element solution. And when nx and ny are equal to 100, number of elements is equal to 19,000. And as you can see here, the running time is good, right? And if I increase nx and ny and run the code again, actually, what is the number of elements? When the nx is equal to 1000 and ny is equal to 1000, number of elements was equal to 2 times nx minus 1 times ny minus 1, right? So this is 999,999 times 2. This is the answer. So this is really a big problem. Number of elements is equal to 2 millions, right?
Yeah.
And as you can see here, we can solve this large problem. This is really a large problem. 2 million mesh elements. So, however, the geometry and problem is simple here, but you can solve a two-dimensional problem over 2 million mesh elements in MATLAB in few minutes. This is important. Okay, so do you have any question about the code?
No, as of now, I'll just go through once again that if there are any queries, I can do it.
Yes. You need to review the code step by step because I didn't write the code using for loops. We wrote the code using for loops in one-dimensional problem. But here I used index programming. Index programming is really good. Our code is really clear, right?
Yeah.
So you should read about the bit or function in help. I don't want to waste the time here, right? You can read more about these functions in the MATLAB help. So we constructed the stiffness matrix and we applied boundary conditions and we solved the problem, right?